In this video, I'm going to give a brief overview of electric charge and Coulomb's law. So in mechanics, we would have problems that dealt with objects that had a mass, and these objects were subject to a gravitational force. Now we're going to move on a much smaller scale to things called particles, and these particles have charge, and they are subject to electric forces. Now we hear about charge in our everyday life. There are two main types of charge, and I'm going to demonstrate this with an example. So let's say you're holding a plastic rod. Here we have a plastic rod, and you're holding it in your hand, and you happen to have a piece of fur. Now let's say you rub the fur along this plastic rod. What's happening in this case, as you rub the fur along the rod, is that electrons will move from the fur to the rod, and the rod, in this case we'll call it, becomes negatively charged. So basically it has a negative charge. Electrons have flowed from the fur to the plastic rod. So now let's move to a scenario where we have two rods next to each other, and they've both been rubbed with fur, so they both have electric charge. The two rods will want to move away from each other, and we often call this that the rods will repel. Now, in other experiments, we'll have our plastic rod again. This time we're going to rub it with silk. And now with silk, if you rub the silk along the rod, electrons will flow from the plastic rod to the silk. And so the rod will become positively charged. It's positive charged. Now let's say we put a rod that has been rubbed with fur, so it is negatively charged. And let's say we have a rod that has been rubbed with silk, and it is positively charged. These two rods will move closer to each other, and we call that attract. So move like this. In this case, these rods will move like this. So this demonstrates we see two types of reactions between objects. We'll see them repel, or sometimes we'll see them attract. And I did not spell that correctly. We'll see them attract. And in cases where they attract, they have different charges, unlike charges in cases where they attract. And in cases where they repel, they have like charges. So in this situation, we'll call that like charges. That's kind of what we mean by charge. Now in this scenario, I had a plastic rod. Plastic is one type of insulator. Insulators are materials that do not permit easy movement of charge. Another example is rubber. In this case, let's say this rod was metal, like iron or copper, and we rubbed it. Well, it wouldn't become charged because metals allow charge to flow through them really easily. And so if we're holding this in our hand, even as we're rubbing the rod with fur, the electrons would flow through the rod, through our hand, and into the ground and into earth. So it's another key concept is insulators and conductors. And so materials that let electric charge flow easily through them are conductors, and common examples of that are most metals, such as iron, copper, are two examples. Insulators are kind of the opposite. They do not let electric charge move easily through them, so charge can remain on their surface. And examples of this, one prime example is rubber. Now, another good example of charge that we see in our everyday life is when we do laundry. So inside the dryer, when the clothes kind of move around and they rub against each other and against the metal inside. And so electrons are flowing from one clot to another. So some of the clots become positively charged and some of the clots become negatively charged. So that's why when the dryer shuts off and you go to get your clothes, a lot of the times you'll notice that clothes stick together. And that's because the clothes have acquired unlike charges between them. I'm gonna clear this page. Kind of the next main concept with charges is a law that describes the interaction between particles and kind of describes the force. So we call this Coulomb's law. So the force between two particles, let's say we have like a particle here, it's a positive, and another particle here is negative. And there's some distance between them that I'm going to call R. Well, this law says that the force between these two particles is a constant K, Q1, which is the charge of particle 1, and Q2, which is the particle of charge 2. So the magnitude of those charges, Q1 and Q2, and there's going to be an absolute value, and I'll explain that in a second, over R squared, and R is the distance between them. So K is a constant, so if we're using SI units, K is often 8.99 times 10 to the 9th newtons meter squared per Coulomb squared. Where the C is, it's not Celsius, but the C is Coulomb, which is a unit for charge. Unit for charge. And this equation is mainly for instances primarily when your particles are in a vacuum, or that there's not any material between the particles. Vacuum. Oftentimes air, if you have a situation where the particles are in air, it is okay to use this equation. So kind of one conceptual example where this kind of law doesn't work is, let's say you rubbed a balloon against someone's hair. So that balloon becomes charged. And let's say we stick it against a wall. Now the wall is an insulator. And so the balloon will stick to the wall, but no electrons will flow. But what will happen is on the wall, the charges will align themselves so that, we'll say that let's say the balloon's negatively charged after it's been rubbed by someone's hair. The particles on the wall will align themselves so that the positives will be as close to electrons as possible, and the negative charges will align themselves on the outside. Now you can see that here there's a force, an attraction force, between the negative and positive charges. Now since the negative and positive charges are closer to each other, this R value is smaller, and so that value will be bigger. So here we have the total force. There's an attraction force And there's also repulsion force here with these negative particles. But because the positive particles are more closer to the negative particles, the traction force will be greater than the repulsion force, and that is why the balloon sticks to the wall. And that's another reason for the absolute value of this. This force here will work, it is for both attraction and repulsion forces. And so no matter what the sign of your charge is, you take the absolute value. And after you have the value of your force, you need to go back to the problem and look at the signs of the charges. And that will help determine what direction the force is in. So this equation kind of lets you find out the actual number of the force, and then you go back to your problem to figure out in what direction the force is acting. So the next few videos will go over problems that relate with charge and Coulomb's law.